Hey everyone, I'm Zach, and I'm going to present my project on the GPU Accelerated Occupancy Map. Start with an intro for anyone who's not familiar with it, and then I have a couple videos and demo that I'll get into. So first we'll get into the motivation for this, and my motivation was from an old mapping algorithm from an Intro to Robotics class I took at JHU last spring actually. This was a recursive quad map implementation, and that was to save memory. You'll kind of see in the demo in the later slides how that does that. But the thing was, it was slow. One, it was in Python, and two, it was all sequential and recursive. So it was pretty slow, and I didn't think it was, very applicable to putting on like a real-time robot. So I wanted to look into figuring out how I could parallelize that. And then here's a quick demo of the Python code, which is in my Git repository as well. So you can see the memory saving features, how on the right there, it had small blocks that eventually get, I guess, combined into larger blocks. And that was big motivation with this particular algorithm. So getting into more of an overview of robotic LiDAR, um, it's really just how robots scan for obstacles. That stands for light detection and ranging. If you're familiar with radar, that's just radio detection and ranging. It's pretty similar, just a little bit more applicable for objects and robotics. There's 2D and 3D approaches, so you can see the map over here on the right, top right here, is a 3D approach of a road, and you get pretty high fidelity, you can see. And then the picture on the bottom here is actually a snapshot of what we did in the robotics class in Gazebo. All of the blue here are the LiDAR beams, and this is our little robot here that can spin around and move through this environment. Even though this, appears to be 3D, we actually modeled it in 2D, so that's why the LiDAR is only flat. If you had, of a 3D modeler like this, the LiDAR would be scanning in all directions. So essentially, as the robot goes along, you get scans. You might have any number of scans, typically, to interval of spacing that you can define. And then within those scans, you have beams. And the more beams you have, the more data intensive your processing is going to be. And another thing I want to mention is this essentially takes a world view and then applies it to a grid view. So the LiDAR input is typically in X and Y coordinates, and then you convert it to pixels so the robot can actually do something with the data. So I'll get into the algorithm that this uses to do that, and I think this should give you a little more explanation on what's going on. So essentially we have three states. We have unknown, occupied, or unoccupied, and that's how the robot fills its map in. So it knows its location, and it's really scanning for hits. In this case, I don't have a LiDAR sensor in this, so I already have data that has hits in it. So mine, in this case, is just looking for those hits. And pretty easy, the hits are marked as occupied. The rest of the points along that line are marked unoccupied. And before it gets to it, they're marked unknown. And as you can see on the right over there, this is how the robot, I guess this is just really a line algorithm in general. This can apply to computer graphics or robotics. But you can see where if you had a robot, say in this location, and it got a hit over in this cell, that there's no straight line path to actually get there. So the line finding algorithm essentially finds the best number of pixels to get there. So getting more into my implementation and the algorithm that I use, You can easily parallelize this for real-time robotic scenario. Um, you can use a flat map to be GPU friendly. So like I mentioned, the recursive quad map before. I did not go that route. I thought that would be a little too complicated. I'm sure there are ways to do it. But instead of saving space with using larger blocks, I just decided to use a small integer data type to keep the grid small. So even though I have a lot of blocks, potentially that are just unoccupied space, at least they're pretty small. From there, you feed each scan into a GPU kernel, at least this is what I'm doing, that runs a Bressingham line algorithm for each beam. And one thing I didn't realize at first, it's been a while since I took this class, but the really the only parallelizable part is the beam number. And that's really where the GPU shines. If you're using this in a kind of real-time scenario where you're only looking at, one scan at a time, the scans themselves you can't parallelize because you wouldn't know where the next scan is going to be. So I have a two-step kernel processes. So first thing I do is mark endpoints kernel, and that just marks all the endpoints as occupied in one step. So I read in the LiDAR data, look for the end of each beam, and then I mark that as occupied. And you just all in one go. And the next step is the ray tracing kernel, which this is what's actually running the line algorithm on all the beams. And even though this is very parallelizable, you do run into some warp divergence because you don't necessarily know how long each beam is going to be. If you have walls that are closer to others, um, it's going to potentially take longer time to run. There are some techniques that I could have done to try to optimize that, but the timing that I was getting out was good anyways, and there's only so much scope in the project, so um, I can get more into my results on that later. The biggest challenge with this was, I would say, the ray trace is that some beams might pass through the same cell. So like I showed on the previous slide, I'll go back to help this make sense. If you have a robot right here, um, and maybe it picks this cell now instead of this one, because maybe you had an obstacle here and now you have one here, or here, for example, you're going to run into the same cells. Um, and you have to make sure that you don't mark one of those as unoccupied or occupied as you're going through. It's probably more pronounced on tighter angles, and depending on your algorithm, like this cell's technically in there, so that could be marked gray, and then clearly if you had a line that looks like this, um, that would be marked as well. So you have to make sure you're not overwriting the same cell at the same time. And luckily CUDA has a function that can help with that, atomic CAS. And essentially what that does is it reads the previous value, writes a new value, and then compares the two. By the two, it compares the return value to the previous value. And if it doesn't equal itself, then that knows that another thread changed the memory. And a typical CUDA, I guess, design pattern with that is to just put it in a while loop until it succeeds. I thought that was kind of weird, because atomic, to me, coming from C++, typically it's just guaranteed that you don't have to worry about it. So I thought it was interesting how CUDA handles that. I didn't look too far into why it does it like that, but I imagine the internals get pretty complicated. So looking into the dataset portion of this project, originally I found an Intel LiDAR dataset that I wanted to use, but I really couldn't figure out how their coordinates were implemented. They had some Python files that were, loosely documented. I'm sure I could have stared at them for a while and figured out how to parse them, but that seemed pretty difficult, especially because the data portion wasn't really the part that I wanted to focus on. I kind of just wanted some data. So I actually used Claude to help generate new data sets, which was very helpful because, you had all the code. I could kind of tell Claude what I needed in the data format that I wanted, and it was very useful to help generate some basic scenarios. I could have done this by hand as well, but that would have also been pretty annoying to plug in all the um, robotic paths and walls that I wanted in there. So Claude was a pretty useful tool for this particular portion. And the data format that I'm using is there's just a pose and a scan in the data set, and the pose is just your x x position, y position, and theta, so your angle, whatever direction the robot's looking. And then you have your scan, which is just a vector that I have hits, and then hits is just where in the world frame, looking at it from the perspective, you got a hit, which would be the red in this case, so any place you have a wall. So I'll jump over screens here to a live demo. And here, this is my project. So I think I had some old commands sitting in here already. I already have it built, so you don't have to wait for that. But I have this generate test data HD. So from the previous slide, this would be the portion. This was the image on the right-hand side. I also have a just regular generate test data that's more simple, uses less beams and that sort of stuff. So I use the HD to get a little bit better GPU performance analysis, I suppose. So that takes a little bit to run, and then we can go ahead, and I have two occupancy map algorithms. So I have a occupancy map CPU, which is just all implemented in the CPU, and then you can go ahead and pass your test data to that. You can see that runs. This was the biggest amount of beams that I tested with. I believe this was 100,000 beams, and we get about 9.8 milliseconds per scan. And then that actually spits out what you can see here, this PGM file, just a black and white file format. I never heard of PGM, but it seems pretty standard for these types of maps. Then I have script over here, so if we can just go ahead and run Python, and then I visualize maps, so you give it the data set that you tested with. So let's see, what did I call that? Demo test data. And then you give it your output PGM, which I believe is called this, yes. And you can see that plots your both your input file that you saw from the previous slide and what your PGM is. So it kind of gave me a good validation of what's actually happening for the robot. And then same thing, that was the CPU version, so they do the exact same thing. I also have a CUDA version that can do the same. So we'll go ahead and run that. You can see I'm just sitting on my laptop here in WSL environment. And it's a good bit faster per scan, especially if you have a lot of scans that you have to do, or even a much larger data set than this, that can significantly improve your runtime. And then just show you that this also works with the CUDA version, that I have the same outputs. We'll go ahead and run this again. And as you can see, another good verification here. PGM matches, what our LiDAR input looked like, so we're good to go. Back over to the slide deck. Going to look at the timing analysis there, so you can see in my terminal I had some timing runs. I'll just get into those a little bit. So the CPU per scan timing was about ON, which makes sense because that's what the line algorithm claims to be. And it looks almost exactly linear, kind of exactly what you would expect. The middle one here, the GPU per scan, this was interesting, and I left the data like this on purpose. So whenever I did this, I think I actually worked backwards. I started at 100,000 beams, then walked down to 40 or 60,000, and then to 16,000, and then back to, I think, 180, just a really small data set. And what you'll notice is the GPU kind of has like a threshold. So if the kernel is actually doing a decent bit of work, you'll notice like a legitimate timing score. I should mention my timing, I did not use CUDA's timing. I used just a CPU. I believe I used Chrono for this. So if your kernel runs for long enough for the CPU to time it properly, you have pretty good timing numbers, and I think this makes sense. It's not going to scale linearly on a GPU because it's very parallelizable, but it will take a little bit longer because you have a little bit of overhead from the CUDA scheduler. But what's interesting is that if the kernel runs so quickly that the CPU timer can't really do anything, you just get like erroneous data. And I had to look that up. Apparently, that can be anywhere from like 1 to 4 milliseconds reported from the CPU if the GPU kernel just runs too quickly. So I wanted to leave that in. I thought that was pretty interesting. You can get rid of that if you use CUDA timing primitives, but I thought this was a little more useful as an apples to apples comparison and really kind of shows that, below a certain number, the GPU is just not worth it at all. And then over here we have our CUDA total scan time. I plotted this one just so you could see this is just an anomaly of uh, the timing libraries I was using. And this is, kind of exactly what we expect here. Again, not linear, but um, not flat either. So I had a handful of takeaways on this project. Overall, the robotics portion was significantly more challenging than the CUDA portion. Um, I kind of picked this project because I was interested in the old robotics that I did, but that was definitely the more difficult part, getting the coordinate frames to line up, getting the data was difficult, um, and all that sort of stuff. The CUDA itself was really pretty simple. You could go ahead and look at the kernels in my code. There's really not much there. The Bressingham ray tracing kernel is a little more complicated, but again, that's a pretty standard algorithm. Um, and really, the biggest learning piece here, I would say, would be the atomic CAS function. That I thought that was pretty cool. How you can, still get parallelized efforts even if you might be looking at the same portion of memory. So what is good, I hit a lot of the main goals of the proposal. I was able to flatten the map for CUDA acceleration. I was able to implement a multi-kernel approach for code iteration. So originally, I wanted to map those. I wanted to create that first kernel that did just the occupied marking, and then I wanted to go ahead and implement the ray tracing kernel. The timing analysis was also very useful to look at. I think it gives, pretty good real-world example of why GPUs are useful and when they're useful. And then I was also able to get a basic display GUI for validation. I don't really know how I would have validated this without a GUI. I mean, I could have, I suppose, compared the raw data like line by line, but that would have been pretty difficult. Other thing I want to mention there with the CUDA that I think I mentioned earlier in the presentation is there are some ways I could have even further accelerated CUDA. Um, One would be sorting my beams by occupied length, I suppose, like how long the hits are. And that probably would have helped with some warp diversions because there's a while loop that sits in my kernel right now. And if I could have batched those to similar warps by length, that would probably have helped um, from warps waiting on each other if they're taking longer to run. Another thing I could do is kind of do it pixel by pixel and schedule it from the CPU and just let the GPUs iterate on a pixel by pixel base. I didn't completely follow that approach, but I think that is more um, in tune with, really performance optimizing. So I didn't meet everything though, like I wasn't able to use the Intel dataset. Unfortunately, they didn't really have much documentation on it, and I didn't want to spend a lot of time searching for another dataset that was vetted through. So luckily Claude came in and I was able to use that for, still pretty good overall analysis. I also wasn't able to get a real-time display with OpenGL. I would like to look into this. I think that would be pretty cool if you could see the map kind of get created dynamically as you went, but unfortunately didn't have time for that. And then third one here, the log odds approach. I kept it basic with the 3 state maps. The robotics portion of this was, pretty heavy and I don't have a big background in it, so the log odds was kind of a little bit over the scope, which is okay because I think there's still a lot of good takeaways. And biggest thing I learned like I said, a kind of incorrect assumption I made coming in, is this approach is much more applicable to 3D LiDAR processing or processing scans as batches. So the CPU beat this algorithm under, I think it was, I forget, I'd have to look at the time exact, but it was either 40,000 or 100,000 um, beam samples. And 2D LiDAR processing doesn't really use that many. I think I saw a number of like 1800s pretty standard. And in this project, I was only using 2D. So my inflated beam data to get my GPU to beat the CPU is kind of unrealistic. Now, if you had a 3D LiDAR processing pipeline, that would be a lot more realistic because I believe, those average around 100, 200,000 beams per sample. So it could be applicable there. I also see this being very applicable in post-processing, so kind of as a validation of what the rate of what the robot might have returned, or if you had a fleet of robots, so you had to analyze all their data. Instead of doing this sequentially scan by scan, you could just, instead of parallelizing just the beams, you could also parallelize the scans, which would significantly improve how long your post-processing took. So that's all I had. Anyways, good project. Hope you guys enjoyed looking at it. And yeah, thank you.